And I would like to introduce you to Emily Winters. She'll be doing our presentation today. So Emily, I'll pass the ball over to you and you can take it away.
Hello. Do you know how I can share my content, because it's not letting?
You should be able to now.
Okay, fantastic. So, hi, I'm Emily. I'm on Team Ignite. I'm a senior. I've been on Team Robolines, Team Ignite, but I love electronics in FRC. It's what made me sort of get hooked in to FIRST. So I'm gonna go ahead and share my screen here. It's gonna sort of be like passing between a PowerPoint and kind of like, if any of you guys have seen Sal on Khan Academy, how he draws on the screen as he explains, I'm gonna kind of do that format. Okay. And I'm Emily. This is FRC Electrical Basics. And then on my other screen here, I've got sort of like a drawing platform. So I'm going to go ahead and erase all of this stuff so we can make room for, as I introduce each part, we're going to go ahead and add it to our schematic that we're going to be creating. The schematic right here. Okay. So again, this is kind of what it's going to look like when we're done. If you'd like to get out a piece of paper and draw it along, more than welcome to. So we're going to be learning first what are the different types of wires, the parts, how these parts go together, and ultimately how the power and information gets distributed all throughout your robot. How everything that's in the battery and all the code you write, how it actually gets to the motors so everything functions properly. So the main three types of wires we're going to be looking at today are your power, your information or CAN, and your Ethernet. And so the red and the black ones, they are carrying all power from the battery to every other device on the robot. So if it's red and black, mostly it's power. There are some few other colors will go along. These CAN ones, these share the information. So they carry the signal to everything that needs it. And so we'll show you where they go later on. And then finally, the Ethernet has a few specific purposes. So these are three main basic. So we're going to start with our battery. It is our, I believe, 12 amp hour battery. It has the two terminals on the top, the positive and negative or ground. And so it just supplies all the power, kind of. So we're going to draw it like this. Start in this corner and add our battery. Yeah. We've got our positive terminal, and you'll understand why I'm drawing it in this specific direction in a little bit. So then, the second thing is our main breaker. Most of you probably know this is very important in robotics. If anything's going on in the robot and you need to quick turn it off, you want to hit that red button. So it intercepts, or it goes in the middle of the positive line coming from the battery, so that when you press the red button, it disconnects that power wire so that there's no more power being supplied to the robot. And then when you want to turn the robot back on or continue the power flow, you want to hit this black switch right here. I can't hear from any of you, but I'm going to assume you can see my cursor on the screen. So fantastic. So that's why we have this red wire over here. We're going to real quick draw the main breaker, or the circuit breaker, if you will. So it's got sort of this, that's white. Got our red sort of button you press, and then our black switch, like that. And so then it continues up here as well. So we've got almost a complete cycle of power. There's one more piece to this. And anybody can let me know if I'm going a little bit too fast. we've got our power distribution panel. So it's got 16 different slots on it. And so this is what takes the power coming in from the battery as an input, and its output is in specific amounts. So you can't just have all the power from the battery running to every specific motor. You want to sort of siphon off a little bit to each motor. And so we'll get into how that works in a second, but it's got 16 main ports. It's got 8 for larger gauge wires, which would be a smaller number wire. And then it's got 8 ports for sort of smaller wires, which would be a larger number gauge. And so usually these larger ones are for 40 amp and the smaller ones are for 30 amp. However, the motor controllers we're going to get to in a bit, you want to bring the power to your motors, they can go in either port. So like your Talons, your Victors, they can go in either one of these. So this connects to your battery circuit. And I'm just going to label it PDP, or power distribution panel. This is sort of the end it connects to your battery. And then you've got your 8 sort of ports over here and your 8 sort of ports over here. And then over here it has some more connections that we'll get to in 1 second. And then over here is its CAN attachment place. So once we get to the CAN circuit, the PDP will be a major stop on that. So next we get to our motor controllers, and there are many, many kinds. There's, I've personally only worked with Talons or Victors, but there's Spark, Max. These basically, they control the amount of power and at what times it goes to your motor. So let's say you're driving in a match and you press a button on your controller. At that specific time, you want to give your motor power. You don't want 40 amps of power just running to your drivetrain constantly. So they have CAN wires attached to them, so they know your code and they have the power, so they sort of dictate your motors when to go, how much and when they need to. So we're going to get to all of this potentiometer encoder if we have time in the end. That's sort of not so basic as this course is titled. So if we have time at the end, but I want to leave lots of time for questions. So these connect to the PDP slots and then they go out. So we're going to draw 2. These are our motor controllers. So we're going to draw, let's say, a Talon and a Victor. Actually, for purposes of this, we're going to draw 2 Talons because they have some capabilities that we'll gonna touch on a little bit. So Talons are a bit more expensive than Victors, however, they have some more capabilities that come with them. So we'll get to that later. There are Talons, and then those different colored wires I mentioned earlier. These power wires coming off the Talons are green and white, and that's just for easy identification. They're the exact same as the red and black ones over here. It's just so that you can easily identify which are coming off your Talons. So we're going to model sort of a drivetrain here, 2 sim motor drivetrain. We're not going to get into motors or gearboxes because that sort of branches out from electronics. So we're just going to do 2 sim motors to see how it would kind of work. And so this drivetrain has 2 sim motors driving 1 wheel. So you'd have some sort of gearbox over here, driving wheel, whatever ratio you'd like. But this is just how it works from the electrical standpoint. So each of these Talons control 1 motor so that when you give it a signal, it knows. So that signal is going to be part of the CAN system we're going to get to later. Right now we're just focusing on the power. So next we've got our radio. So we started with the battery and we sort of branched out from there. Now we're starting at the code where the robot connects to your laptop. So this kind of works very similar to your home Wi-Fi router. It actually has a little light that lights up if it can connect like Wi-Fi router. And so on your laptop, you would go to the exact same place you go at home to connect to Wi-Fi at your house or at a Starbucks. And so you can give it a certain name, and so it'll appear. And so this is how your robot sort of gets the signal from your laptop, so that you're not having to run a gigantic Ethernet cord across this match while you're playing, because that'd be dangerous. Okay, so it connects to the Roborio and VRM. We get those in one hot second. Right now, we're going to just draw it up here, over here, radio. And so I'm going to draw this sort of Wi-Fi-esque signal to show that, let's say you had some sort of laptop over here, and you have the code on the laptop, it can receive those signals. And so next we have the VRM. And so unlike our Talons, which get their power directly from the PDP, the radio needs another step, and that's our voltage regulator module. It's because the PDP can have fluctuations in voltage or current as the match goes on, but the radio, since it's in charge of all your connections, so if your robot loses connection during a match, it's usually something to have to do with radio. And so we want it to be as regulator as possible. And so the VRM can be used for a myriad of things that also need more regulated, consistent voltage. But right now we're just going to get into the radio. So connect the power, and then these three slots I talked about earlier, one of these is for the VRM. We'll get to the other two in 1 second. So this gives off, you can see in the picture here, it's connected, and so it gives off 12 volt to amp power to the radio. And so many times you might want to connect it by Ethernet. This is power over Ethernet. And so these two power wires are put into an Ethernet casing, an attachment point. And so that's the main purpose of the VRM. Moving on. We've got our Roborio. And so this is sort of the main, like, if any of you guys did FLL, this is that like Lego Mindstorm's brick in the middle where you go to select your code. Except when you push all your code onto your robot, it's stored here, and then it just uses specific commands when you're driving a match, say with an Xbox controller or joystick. So this is where once the radio connects to the signal of your laptop, it stores the code in the Roborio. So we're going to connect it to the radio and place it up here. And so I'm going to use a blue for these Ethernet wires, just so they stand out a bit. And so you could, one solution is just to connect it like that. The signal is being stored here, the code. Or you could do something called a network switch. So everything that uses Ethernet on this robot is actually connected to the radio. So let's say you had like a vision system and the Roborio and another vision system. That's too many. So you can add a network switch, which just basically gives you more Ethernet ports. We'll draw it right here, network switch. And so then if you have anything else in the robot that needs that Ethernet, let's say, I'll put it right here for a bit of ease. And then anything else that needs it, you've got more ports. That makes sense. So like a Limelight would need one of Ethernet ports. All right, so that's it. And then one of these slots over here, it's powering the Roborio. Real quick. So now we've just got one main piece, and then we can go ahead and put the CAN wire to show you how this code that's stored in the Roborio is distributed about. Before that, we have the RSL. And RSL is very, very important, especially if you want to pass inspection for your robot. So the RSL tells when the Roborio has power. So it's connected to the Roborio in this RSL port right over here. And so when the Roborio gets power, say when you turn the robot on, it lights up orange. And then when you enable your robot, let's say on a practice field or during a match, it'll start to flash. And so if you ever go to work on the robot and it's flashing or it's on, you might want to double check before you stick your hand in it. So it has to be in a very visible space. Anyone on the in the arena can see if your robot's enabled, because it might shoot out a power cell across the field and hit someone. So this is connected directly to the Roborio, and it just tells you if the Roborio has power. Because if the Roborio has power, that means the power has traveled all the way from the battery, all the way through the PDP, all the way to the Roborio. You might have a broken talon. You might have a CAN issue. So the VRM might be unworking. Well, that would be very unlikely. But the Roborio has power.
Emily, we have a question. What does RSL stand for?
Robot signal light. I'm going to do some lines like this to show that it is glowing. So don't mistake, a common misconception is that the RSL means that your robot's working properly. You could have all the code broken, all your talons are broken, none of your gearboxes are working, but as long as the Roborio is getting power, it'll turn on because the robot now has the capability to do something with the code that it has. And then I believe our last component, so this is a really old image. I believe it's from the first FRC handbook. It's kind of neon and warped, but there's a better image on the next. This is the pneumatics control module, or the PCM. So we're not going to get into pneumatics in this lesson, but any pneumatics components you have, say a solenoid or your air compressor or your the switch, regulator switch, the emergency switch for your air compressor, these all are plugged into here. And so unlike motors which are connected to talons, any pneumatics components are plugged in here. And this just gives a different voltage of power. That's why. So we can draw the PCM next to the VRM, sorry, pneumatics control module. And so I'll just draw a few. These are going to kind of overlap, but we haven't overlapped any wires thus far, which is fantastic. So I'll just draw a few examples. We'll draw them in white. So you can have solenoids, your air compressor, and then your switch. So if you know anything about pneumatics, that's kind of how pneumatics fits into here. And so here's a much better picture. So here is some of the CAN system. So we're going to start drawing our CAN wire system. So a lot of you, I'm guessing, could kind of guess it's going to start at the Roborio, because that's where the code is stored. That's where it's leaving. And so you've got to go to all the talons, because they need the code to know when to distribute power to the motors. They're kind of twisted around like this. And then you're oftentimes going to connect them. Kind of a black clip right there. You don't really want to solder them together, because the ones connected to the talons, they're made by the manufacturer. It's really hard to make them longer. So you kind of want to prevent trimming them down as much as possible. Then the next thing that needs the information is the PCM, because it's got to send those instructions to the solenoids, air compressor, anything that needs to know when to function. Like the VRM can function the whole match. It's sending constant power to the radio, but some things need more specific instructions. And then, well, it gets kind of complicated. It ends over here on the PDP. So we've got our start and our end point. Kind of goes in one big, I'll do it like this for right now. I'll erase this when we're done. This make it a little bit more transparent. So we've got kind of going like that. So it doesn't form a full loop. It's got a start point and an end point. There we go. Fantastic. Any more questions? Are we all good?
No other ones other than the fact at the end of the presentation, can you share the slideshow?
Yes, I'll try to find some way to do that. Okay, so no questions. We're going to get into a few additional items. There are so many variations, but these are the ones becoming increasingly popular in FIRST robotics. So I thought I'd explain a little bit about how these specific ones might work. So we've got some vision tracking and some inertial, this should be measurement. I'm so sorry. Inertial measurement unit. Not quite sure why that says mass, but it's going to show how these work in conjunction. So I wonder if you guys can see this. Move this out of the way. Move this. Oh, we're going to put it over here. So we've got our roll, pitch, and yaw. Let me move my face. I don't know if you guys can see it. Roll, pitch, and yaw. So these are the three directions. If you imagine a robot instead of this plane, most of the time we're going to be looking at the yaw of the robot as it turns right or left. Not a lot of robots are going to be rolling over or pitching forward and backwards. You could use pitch if, say, if your robot started to fall over, if you had a really tall elevator, you're like, if the robot starts to fall over, bring the elevator down to lower our center of gravity. Or vision tracking, or just finding objects in the field.
Emily, we lost your video. Your audio is muffled.
Oh. Is it better now?
That's good now.
Okay, great. So the IMU knows the robot's relative position. And so it's super important during autonomous. I'll sort of use a scenario to describe this. Let's say in autonomous, you wanted your robot to make a series of moves to end up at, the rocket ship from deep space. But one of your gearboxes is a little rusty, a little worn down. So each turn, it turns a few degrees less. So by the time you finish autonomous, you're way off. You're nowhere near the rocket ship. You're driven drastically off course. So if you use the IMU, and we're not going to get into the code aspect of this, it knows the robot's relative position. So if the robot goes to turn, and it didn't turn exactly how much the code dictated it to, and so this is kind of a code thing, but in the build aspect, it will make adjustments to the robot so that it ends up at exactly the precise position the code would like it to go to. And so this is one of the reasons why we have a Talon. So the Talon has a little port on the top right here. And so we're going to place the IMU just over here. Since it does measure your robot's position, you normally want to put it in the middle of your robot, either front to back or side to side, so that when it turns in place, it knows it's turning in place and not moving around an arc. But it can attach, the wires are kind of beige-ish, connects to a Talon. Or if you have, or also connect to the Roborio. I know there is an IMU NavX, and there's a Pigeon IMU. A Pigeon more likely connects to the Talon, and a NavX can connect to either one. So that's one reason we have a Talon. Something else that can help with the robot's just positioning is called an encoder. And so an encoder, let's see. Just imagine we have the shaft that these motors are running. We're just gonna place the encoder on that shaft. I'll write it out. So these motors are ultimately using a gearbox to turn the same shaft, and this encoder will be on that shaft in some way or form. And so it counts a number of ticks per revolution. So let's say, for an example, one revolution was 4,000 ticks, or 40,000, I forget, on the encoder. So it knows how much the motors are turning each side of the drivetrain. So programmers can use this knowledge to make sure your robot is driving straight. That 4,000 ticks on this side is 4,000. It's not going 3,000 and 40,000, which would cause it to veer to the right. So this is also connected to the talon. And it's because this talon is getting this signal. And so the Victors do not have a port on top for the spark. So the way this CAN system works is that the Roborio is going to give a signal that's designated for a select port or endpoint. And so the signal is going to travel down, and let's say it's controlling a solenoid. It's going to go to this talon, be like, nope, not me, keep going, nope. And then when it goes to the PCM, be like, yes, this is the designated port I was assigned to. And so then it will control this function. So if something would like information from the encoder, it's just sent to this talon port. And so finally, we have some vision tracking. There are so many ways you can vision track. I'm going to explain the Limelight real quick because I've had a few years of experience with it, and it's super simple on the electronics side of things. I'm going to put it up here. Limelight. And that's the massive green light. If you've ever been to an FRC competition before, you've probably seen a blinding green light coming from the field. That's the Limelight. So it's connected to Ethernet. So again, one of our network switch, we're actually going to use one of them for the Limelight. Bam, and then it just needs some power. So it can go into any slots of these PDP. We're going to be crossing the little wires. I hope it doesn't get too confusing, but it can go directly into a PDP port. And that's one of the fantastic things about the Limelight. And so I put it into these ports over here because these are the smaller ones. And so this Limelight, a larger gauge wire is smaller. So these wires are too large of a gauge to go in these. These ports are too big. If you tried to put it in one of these, it would just, some of the wires or copper pieces would fall out. So the Limelight can use information from the IMU or encoder or both to position your robot towards a target. So it can adjust the yaw if you'd like, rotating left or right, so that your robot can perfectly line up. We'll use the same rocket ship. Here, it senses that reflective tape, and it can be like, in order to get this reflective tape in the center of my camera, I'm going to rotate the robot to the right. And if it overcorrects, it can rotate back to the left, but that's kind of how, one example of how that works. So a lot of the vision systems we use in FRC are fairly similar to this one. And so the IMU and encoder are just two ways. The encoder can also have different uses. Let's say you had an arm you wanted to lift a certain amount each time. You could program it to move a specific number of ticks. Okay, so do we have any major questions on that one? Because we're going into sort of the second part of what we've got.
The only question that we still have left open is someone asked, do all of the CAN wires, are they all connected? Do they all connect?
The CAN wires, they all connect. They don't form a full circuit, so it sort of has a start and a stop. So yes, but these are intertwined together, and we're going to connect them all with the black clips I showed. I should really draw them all just like that. And I can also share this drawing at the end of the presentation if I'm able to. Cool. So now you know all the parts. It's a matter of knowing how to put them together, how to connect the wires to their specific ports, So the first thing is cutting and stripping wires. This is very important. Here I've shown a manual wire stripper and a sort of self-adjusting wire stripper, so you don't need to know the wire gauge per se. And so when you it depends on what you're cutting a wire for to depend how much you want to strip off. So depending on different types of connectors we get to, you're going to want to strip off a different amount of that insulation surrounding the copper wires. And so this one is a manual wire stripper. So it has, you see the different holes in it, the red handled one, they all have different numbers by them. So you want to line up the hole size with the gauge of your wire. And then you're going to sort of put it around the wire and then pull off the insulation off. And this one, my team calls him Jerome. He's the self-adjusting wire stripper. You put the wire through right there, the blue and yellow handle one. You put it right through that opening, and then you're going to squeeze the handles together, and the two metal pieces on the top will come down, pierce through the insulation, and then take it off. And so I'd love to be able to do this presentation in person, let you all try it out for yourselves, but we're making the best of these times. So these are ferrules. Those are the first connector we've got. For these, you're going to want to strip about 1/3 to 1/2 an inch off your wire. It really depends on the size. You see on the image in the top right corner, the silver metal part on the top. I'm not sure if you guys can see my cursor, so I'm going to explain which image I'm talking about. The length of that metal piece on the end of the ferrule is the length of the exposed wire. You want it to be exactly that length or as close as you can get. It would be preferable if it was like 1 millimeter longer rather than too short. So it's super simple. You strip that amount of wire. You're going to put the wire into the ferrule coming from the side with the insulation, so the colored side. You insert the wire from that end. You're going to make sure that it is pushed as far into the ferrule as you can, and then you're going to place it inside of a crimper, and we'll get to that later, but you're going to place it inside of the crimper and just squeeze the handle. So do I have a, oh, I apologize. I totally don't have a picture of a crimper, but it's a tool that has a square in the middle of it. And so you insert the ferrule into that square, and when you squeeze the handle, it'll sort of crimp or impress the ferrule onto that wire in a square shape pattern. So then we've got the Anderson connectors. There are these red and black one over here. So we've got the contacts, which is a white silvery bits, and then you've got the housing, which is the red and black, more so rectangular pieces. And then you've got the retention clip, which is a black clip that holds two housing sets together. So if you have a connection, you place a retention clip on it, and it's used from, let's say, a Talon to a motor, so that your Talon doesn't accidentally disconnect from your motor. So it works super similar to the ferrule. You want to strip off enough wire to fit inside this main body of the contact, just sort of so that no exposed wire is sticking out, but that it reaches the end. And then you're going to place it in a crimper again and make that square shape pattern. And then these sort of hooks on the end of the contacts, they're placed in, we see the second image down of the Anderson housing in the right end. Coming from the right, you're going to hook them in. It's much better to see in person. They can only go one orientation, up or down. So if you see, these are all the third image like facing down. They could be facing up. So you're going to want to slide them all the way in until they click. And so if you place them in the wrong orientation, they're not going to click. And so you're going to want to just take them out, flip them over, put them back in. I can't really show you guys the right way to do it right now because I don't have any in person. I'd love to. But those are the different parts. So once you put your red wire in the red housing, your black wire in the black housing, the two just slip together. So they're going to connect. And then you want to do kind of a pull test to make sure it really clicked in place. You're going to want to try to yank those wires out of the housing, and if they don't come out, all good to go. Cool. So next we have the Huego connectors. And these are on the PDP. Normally you don't have them anywhere else in the robot, but they're these circular ports on the bottom and then the rectangle on the top. They're sort of the two arrows are pointing to two rectangles, and these are terminals is the circles. So the wire is going to go in the circle, and your tool is going to go in this rectangular slot on the top. And so you're going to want to use a Huego tool. It is kind of like a bent flathead screwdriver with a green handle. That's exactly what that looks like. So you're going to want to place it into the rectangular slot, and then in this circle, it'll sort of, like a gate will almost open. So if we want to go back here, if you have your circle, it sort of has like a gate right here. And so as you place the Huego tool in, the gate will kind of, yes. The gate will kind of open and reveal this empty space in the middle. And so that's where you insert your wire. And then once the wire is in, you just want to take the Huego tool out, give the wire a quick pull test to make sure it's super in there. Do your best to get all the wire ends in that terminal hole, so none of them, because one year our Talon had a few pieces of copper sticking out of the PDP, and so during bag and tag time, in the last 10 minutes when we had a bag, the Talon started smoking because it wasn't, not all the wire was inside of the terminal on the PDP. So super important. One trick you can do is to kind of twist the ends of those copper wires to make sure they all stay together. Next we have the Wiedmuller connectors. That might not be how you pronounce it, but what we're going with, the Wiedmuller connectors. So you're going to want to strip 1/3 to 1/2 inch off your wire again. These are where the ferrules can come in handy. So if you have a ferrule on your wire, it's crimped into that square shape, it's no exposed wire, you just take the wire and you insert it in the port you want. These are these black holes. If you don't have a ferrule on, you're going to want to use just like a small flathead screwdriver and press down the white button that's next to your terminal, and then you'll be able to insert just exposed wire into there. Ferrules are super handy because they make sure every bit of that exposed copper is making a direct connection with the power line. And so, but it is possible to do if you don't have a ferrule. You just want to be super careful. And then again, give it a nice pull test. Make sure no exposed bits, make sure it's connected, you're all good. One bit I'm going to go back and mention if you guys want to jot this down. The small Huego connector, these are these ones on the left. It's 10 to 24 gauge. And then the larger connectors on the right, it's 6 to 12 gauge. Your talons are like 12 gauge wire, so they can go in either one. How perfect is that? And then these Wiedmuller connectors are 16 to 24 gauge, so they're a lot smaller. Finally, we've got one last connection type we're going to talk to about. It's just these screws here. So where the RSL connects to the Roborio, and where the Roborio connects to your PDP, that's not actually correct. It's just where the RSL meets the Roborio. You have to, it has this kind of black box you see, and so I'm going to draw it out so you can see it better here. You have your two ports for your wires. And so over here, you're going to have some sort of bigger screw. If that makes sense. So once you unscrew this, you can take the entire system out, because underneath here, there are some screws that actually tighten them up. So like for the PDP, in the PDP and those Huego connectors where the gate is naturally closed, once you take the Huego tool out, the gate will naturally close, lock that wire in place. For the RSL going to the Roborio, it's right here. You have to screw that metal piece in place so that it clamps or tightens onto that exposed copper. So you actually have to unscrew this entire system to be able to screw in those wires. And that's super important because let's say your RSL light wasn't turning on, you might assume like something is majorly wrong with the battery or the power system. So we want to rule out that it's just this little connection right here to the Roborio. And the end. This is a picture of one of my team, Bennett, I included with his consent. Last year we had so many mechanisms on the top of our robot that we went ahead and just put our electrical panel on the bottom. So you see him, he's kind of like a car mechanic rolling under there. He I'm not sure if he had the best time, but it was super convenient in matches because we could just flip the robot over, take off a polycarb panel, but so now you're done. So how much time do we have left? We have about 20
we've
minutes.
got close to 20 minutes. You've only got one question. Grant asked, is this separate wires and they're just all clipped together, or how do you manage the wires?
For which aspect? For just wires in general?
Yes.
Cool. So you can see kind of in this picture, the Talon wires, they're entirely independent of each other. They're just connected at the Talon and at the Anderson clips. And then the CAN wires, they're entirely separate as well. They're just twisted around each other. So one super important part of this is cable management. You might want to use a lot of zip ties. A lot of FRC teams use a lot of zip ties. So cable management is super important because all the wires are just free and independent of each other so that they're not really connected. So that answers.
So you had a question, what is the best way to organize the wires? What's the best wire management?
Okay. So we can kind of talk about that. So one super important part of wire management is making sure that you have the shortest wire path for all of your wires. I know in this drawing, we sort of, so like, I'm going to use an entirely different color. So if you sort of look over here, this battery, circuit breaker, PDP, it's kind of, we could close this up together and there's no real interference. However, might want to do some switching of the PCM VRM, put the limelight in a different position. You want to definitely plan out your electrical schematic beforehand, whether it's using DigiKey Online or using just a drawing, so that it's mostly just straightforward connections, because if it's like that, you can just take all those straightforward connections. If you have any longer wires, you can kind of sort of like I have right here with my drawing, just sort of tie them up like that. And so, but if you have wires that have to go around the entire robot, that's really when wire management is a huge problem because you have to make sure they're out of any way of moving objects. So the way I found most suitable for wire management is the really, really small, like the smallest zip ties that they make. And then definitely plan out where everything's going beforehand and try to make your connectors on your wire so that there's not a ton of extra wire available. Any more questions?
We're up to date. Anyone else have any questions?
Cool. So if
All right, so it doesn't look like we have any more questions coming in. Let's give them a couple more minutes, and so if somebody comes up with some questions. I did reach out and find out that we hope to post the presentations along with the video, so there'll be a link for you to download it, so we don't really have to worry about sharing it in the session.
Cool. I'm going to try to see if I'm able to share this with everybody. Cool. I've got to go to my settings because I turned off everything for this presentation. We're just going to turn back on some notifications so that I can get that drawing right there. Right here, perfect. I'm gonna save it to my device and then try to be able to share it with you guys. So I'm gonna stop sharing my screen right now. And how do I do that? Can I access the chat? No, we have Q&A.
I've got the chat turned off. You want me to turn it on so you can post that?
Yes, that'd be fantastic.
Okay.
Okay, I don't know. Can I post like a link? Is there any way to share a file in these? Because I didn't see any file sharing in the WebEx tutorial. If I'm not able to, I'm gonna send it to Netta so that when she shares out all the PowerPoints, she can share that image with you guys as well. So, great. I think that's the end of this presentation if nobody else has any questions. I know that lunch is right after this one. So if you guys want to go ahead and grab some lunch before the rest of the symposium, and you guys have been watching for a very long time already, feel free to do so.
Fantastic job, Emily. You did a fantastic job. And you guys can go to the Georgia First Symposium page where you received the email to be able to go to your next class. Emily, thank you for doing the presentation, and thanks for all the attendees.
Fantastic. You're welcome. I hope everyone learned a little something, had fun.